Hello. Well, this is Junichiro Horikawa. If you can hear me, any reaction will be great. Okay, let me check. Hello. Okay, I think it is on live. Right, so hello, this is Junichiro Horikawa, and this is the live stream that I'm been doing weekly to teach a essence of algorithmic design and called as a Houdini Algorithmic Life. And this is the 57th episode for this series. And today's topic is to create a kind of a, as the title say, expandable tessellation pattern using Vellum. So what I'm going to show you is initially going to prepare some parametric pattern like these, which you can control these initial openings by going back to somewhere around here with these parameters. You have an parametric open pattern like these, though what I'm interested in is a bit more physics properties or physics behavior, how these openings will work when it has its external forces being loaded on the part of the geometry. Okay, and to do that I am going to use this parametric pattern with a vellum like these to simulate something like a collision between some random objects and see how these patterns will behave based on this kind of interaction with the other object, and see how you can control its openings based on the deformation of the surface. As you can see, that area of the triangle is not changing, just this connection is changing to make these openings a bit larger to be able to deform in this way. And this kind of pattern is used a lot in recently in fashions, like using computational design to create some computational fabric, to create a computational fabric for fashion designs. It's also being used in architecture as well as a surface pattern, though most of them are pre-computed, I think, or based on the behavior of its material. Like sometimes it uses 3D printers like filaments, sometimes it uses the metals or steels and so on, and couldn't really find how you can simulate it using computers, so I have came out with one of the method to simulate it inside a computer so that you can create any kind of like situations to use this kind of pattern. So that's what's interests me this week. If you search for it in, let's say, Pinterest, if you search for expandable tessellation, I think you should be able to find a similar pattern. Something like these is pretty similar. Which will enable you to open and close the surface or stretch the surface by having these kind of holes. So I guess by knowing the method that I'm going to show you today, you'll be able to create these kind of patterns as well. So that will be my goal. All right. So let me show you how you could do that. And if you are a Rhino and Grasshopper user, you could definitely recreate this in these tools as well, for sure. I guess it's much simpler using Kangaroo. So if you're interested, I could also do something like that in Kangaroo as well. But not sure how many there are. Alright, so let me get started. First thing first, what I would like to do is to create a base parametric pattern to use it for the simulations, which looks like these. Okay, which initially created from a triangle grid. If I go back to somewhere around here, then make the angle 0, then also show up the edges like these. Okay, so it's initially comes from a triangle tiles, which each triangle is 60 degrees on each edge. And if you raise up the angle, or if you rotate these triangles and try to connect each of the edges like this kind of layout, you'll be able to create this opening pattern. Now, this itself is pretty interesting in terms of this movement, but I didn't want to end it right here. I wanted to use this one to actually use it for physics simulations as well. So this is the first step. As you can see, I'm going to start by creating a triangle like these. Then what I'm going to do next is to rotate each of the triangle based on its order. The first triangle rotates, in this case, counterclockwise, and the second triangle rotates clockwise. And this one, the third one, rotates counterclockwise in terms of the rows. For the columns, it goes other way around. If it's the second column, or if it's the second row, this one rotates clockwise, this one rotates counterclockwise, and so on. So based on the number of rows, the index of rows and columns, the order of the rotation will changes. Like these right here. And after I have done these rotation, I'm going to move each of the triangles so that it will come to the corresponding edges, corresponding vertices, so that you'll have a layout like these, using tons of trigonometry, just to remind you. Okay, so this is more of a geometrical parametric method that I'm going to show you next as a first step. Then go to the physics simulations as a next step. Okay, so let's start. I'm going to create a geometry node. Let me save this up so that I don't lose the process. Sometimes the Houdini crashes without noticing. So let me save this up to where in desktop, I guess. Alright. Now, let's start by creating a triangle grid, which I am going to do it in just using a detail wrangle. So that at the same time I create the triangles, I could also create these order for the rows and columns. Okay. attribute wrangle. Then let's see, triangle grid. Then let's start writing this up. Okay, I'm gonna open the editor like these, and I'm gonna start by creating a point information in order to use it for to create a triangle polygon. So first of all, I'm going to define how many numbers of points that I want in x direction. Num x and num y is equal to y Okay, so let's say I would like to have 20 by 20, and in order to do that I need to access to the channel, which is hidden by my thumbnail, which is a bit annoying. Okay, let's set the maximum to 50 for now for both x and y. Let's make it 20 by 20. Alright, now let's start by creating a points on the x direction, or from y direction. Num y. Okay, and let's also do the for loop, another for loop for the x direction. Right. It might be a bit advanced if you have just finished the trigonometry, but yeah, I hope you would enjoy it. Float x. Let's first create the x coordinate by multiplying the I by some specified tile size, so I might need to have the size parameter as well. Then multiply by I by size. Okay, let's try with these. And for the y, you need to have a, if you check the size of the triangles, let's say if I want to start like this triangle, and let's say this is the size, so I'm just going to call it S. Then this is the x direction, this is the y direction. And what I want to know now is this height right here. And I know that the angle right here is 60 degrees for all the angle, for all the edges. So the length right here, the height right here should be, I mean, all the edge has the same size. So that means the height is S multiplied by sine 60 degrees. Okay, so going back, the height is equal to a size multiply by sine of radians 60 and multiply by n, which is because we're in the iteration, or we're in the loop. Okay, and for the x, we need to offset it based on the row numbers. That is because if we have a triangle tile like these, and you probably can see that the point position, these are the position that I'm trying to create right now. And let's say this starts from 0 on the x direction. And for the first column, I mean the first row, it starts from 0. But then for this, from this second row, it starts from the half size of this edge. So you need to define this offset for each like even number row, even row number. For even row number, it starts from 0.5 multiplied by size, then go like these. Then if it's an odd row number, then it starts from 0 again. So going back, the x, I need to know if currently is if the row number is even number or odd number. So to do that, I am going to calculate the remains with n, which indicates the row number, and calculate the remains like these with modulus. And if it's equal to 1, then that's odd number. So in that case, I'm going to multiply this by size multiplied by 0.5 to offset. Okay, should do the job. Apply. Let's check there's no errors. Now I'm going to create a point using those values at 0.0, set x, 0, y used for the z coordinate. And let's see, I also need to give the size as well. And do we have it here? Not yet. That is because I didn't change this triangle grid to a detail attribute or a detail wrangle. So change this to detail. Now you should be able to see the list of points which indicates the outline of the triangle geometry. Now that I've got these now that I got these points, I'm going to connect those triangles or points using 3 points to create these meshes, the triangle mesh inside the same wrangle. Okay, so let's do that. First thing first. Okay. Just in case I might going to use the information like index I or index n, I'm going to have these as an attribute to each point. So set point attrib. I'm not sure if I'm going to use it later, but just in case. Attribute I, which indicates the number of the column at the point to width I. Set point attrib 0 and pt n. Oops. Okay, now let's think about how we could create a triangle from the list of points which we have created previously. So currently we only have the point information, but what we want to have is this outline connecting these 3 points to fill the space with triangles. Okay, and currently in the x direction we have this I value starts from 0, So 0, 1, 2, 3. Okay. For the n, from the y direction, we have this n value, which starts from 0 as well. 1, 2, 3. Okay. And in order to create the triangles for the first column, or the first rows, or the rows on the even rows, you have two types of triangle. One is this one is this one, which has the different orientation. And let's see two of them. The first one, the first triangle has I equals to 0, n equals to 0, and I equals to 1, n equals to 0, and I equals to 1, and n equals to 1. So this will be the first triangle. The second one is the I equals to 1, and n equals to 0, I equals to 1, n equals to 1, and I equals to, in this case, 0, and n equals to 1. Okay, so considering that, and until the end, you have 2, 3, and in this case I is equal to 2, and n is equal to 1. Now, the key point is that for both direction, if I is in between 0 to, let's say, 3, then the number of the triangles on the x direction is 1, 2, 3, 4, 5, which indicates that 0, 1, 2, 4. So 1, 2, 3. So which indicates that this is, you have, first of all, 1, 2, 3, 1, 0, 1, 2, which is in between, one type of the triangle is in between 0 to 2 for the eye, and another types of triangle is in between 1 to 2, and in total you have 5 triangles. And for the y direction, it's a bit more simpler. You have one type of triangles in even number of rows, and odd numbers you have another type of triangles in the same I value, but a different n value. Okay, and opposite directional triangles on a different column. So keep those in mind, and we're going to make these parametric. Okay. So first of all, let's create the condition. So the n and the I shouldn't go over like more than n number x minus 1, which indicates the total number of the x direction. So if, same for n, so if I is less than num x minus 1 and n is less than num y minus 1, then I could create a conditions to pick up 3 points out of these points that I've created for each I and n. Now I need to know the corresponding point number for those 3 points to create the triangles. Currently I don't have any information about PT, but I can estimate this point number because the point number is going to be created from 0, right? And in this case, first of all, the first column is going to be created, the first row is going to be created using this loop from 0 to a number of x. And in the next iterations, for the next rows, the I and this n become equal to 1, then another row is going to be created. So you can say that the point number, the first point number, which corresponds to this point, could be a multiplication of number x, which indicates the number of rows, the number of columns in this case, multiplied by n, which indicates the number of rows. This is the maximum number of points on the in terms of the column, and this is the number of current row number. And if you add it by the current row number, which is I, then this number will be equivalent to this point number that I have just created using add point, because if you use add point, the point will be created from 0 up to the max, the total point number. Okay, so you can convert these n and I to a point number like these as well, which as a result you should be able to get the next point number on x direction and next point number on the y direction as well. So let's say for the next x direction at the same row, is it going to be same multiplication n multiplied by num x and added by I plus 1. I plus 1 determines that you have shifted to the right side next to the current point, going to the right side. So this will going to be the next point positions, next point number on the x direction. Okay. Now it's thinking about the, considering this, you can also try to retrieve the next point on the y direction as well. So let's also do that. pt3 if the row number, which means in this case I, is the same but the row number is different by plus 1, then you can say n plus 1 multiply by num y plus I. What I just did is just replacing this n by n plus 1 to have a next point on the y direction. And last of all, I have another point, which is n plus 1 multiplied by num y plus I plus 1. So in total I have 4 points. Right. So I'm going to use those 4 points to create the two types of triangle. One oriented in this way, one triangle in this way. This triangle and this triangle. Okay, let's try to do that. For the first triangle, I'm going to use this PT1, PT2, and PT3. And probably I need to create those triangle in counterclockwise to make the face of the triangles facing upward or facing to the front side. Was it? No, not really. I might need to make it clockwise instead of counterclockwise. Yeah. So to make it clockwise, the order will be PT1, PT2, and PT3. Let me check. Okay, so what I have just done is using a I value equals to 0 and n value equals to 0, I have just retrieved the 3-point numbers. Okay, one is this point, which is PT1. This one is PT2, which in this case I plus 1. And this one is PT3, which is n equals n plus 1, but I equals to 0. This one is n equals to 0. This is equals to 0. This one is I plus 1 and n plus 1. So I have these 4 points being created. Okay. Now by using those 4 points, I can create 2 types of triangles like these. One can be created, this PT1, PT2, and PT3 clockwise. One can be created PT3, PT2, and PT4, same clockwise. Okay, so let's try to do that. Okay, as the Antonin Triangle is asking why -1, that is because as you are saying, yeah, in order to ignore the last points. Okay, because if we are at this point, then there are no more triangles left on the right side or the downside, so we don't really need these points to start to create the new triangles. Okay, so that's why I have set the conditions to -1, which is somewhere around here for the I, and n somewhere around here. If the n goes far to this point, then there are no more triangles left on the downside, so you cannot really create triangles. You cannot really do I plus 1 or n plus 1, which doesn't exist as a point number. So that's why there is a condition called -1 right here for both I and n. Alright, so now that we have those information, let's try to create a triangles, and we need to separate the triangle creation based on its row order. I mean the row number, if it's even number or odd number. So if if n is first of all a even number, then I'm going to create a first triangle. Let's have the triangle integers to be try1 and try2. Triangle 1 is going to be add prim. It's created as a polygon. Poly. And PT1, PT2, and PT3. Try 2, add prim, 0, poly. So that was PT3, PT2, PT4, PT3. If you count it clockwise. Now for the other direction, when the row number is a odd number, in this case we are talking about these triangles, then that is for these one it has to be this direction, and this has to be this direction, and in this case this is PT1, this is PT2, this is PT3, and this is PT4. So for the first triangle it will be 1, 4, 3, and the second will be 1, 2, 4. Right. Keep that in mind. And let's try to do that. So try is equal to add prim 0, make it as a polygon, pt1, pt4, pt2 or 3. Try 2 is equal to add prim poly pt1, pt2, and pt4. Alright, let's see. If I click apply, and if you see those triangles being created from the points, successful. Alright, that's good. Now, I would also like to set an attribute to these triangles as well in terms of the x direction value, which in this case I, and the y directional value, which is these n, which can be used later on. So let's, in this case, I have 4 attributes to apply: I value for try 1 and try 2, and n value for try 1 and try 2. So set prim attrib k0 I to try 1 with a I. In I direction, if we look at these, since I want to set the I value to be a bit different than the point I value. So the first triangle on the first row, I want to make it as 0 in terms of I. And 1, 2, 3, 4, 5. But currently the value that I have as an I is based on the point. So if I just use the same I value to these triangle index, then the first 2 will be 0, and the second 2 will be 1, and the third 2 triangles will be equal to 2. So in order to make it go from 0, 1 to increase by 1, then you need to change the point-based I to primitive-based I by calculating 2 multiplied by I for this one, and 2 multiplied by I plus 1 for these triangles. The triangles oriented in this case will have this value. The triangle oriented in this way will have this value, and that's going to be flipped in the odd number or even number or odd number rows. Okay, that's for the I, but for the n you can just use the point n value as it is, because it's not shifting to any directions. So n is equal to 0, 1, 2, and so on. That will be just fine. Bit complex, but let's do this. So I multiply by 2, set prim attrib 0 I try 1, try 2, which is the second type of the triangles, which will have I multiplied by 2 plus 1. Okay, now for the n value, it's more simple. You can just say n for the try 1 and try 2 is equal to n as it is from the point. Okay, so let's copy this one and paste it to apply it for try 2 as well. Okay, let's check this out by going to the spreadsheet, geometry spreadsheet, and looking at the triangles, and I want to check if the attribute has been created like these. Okay, looks good. All right. Now let me also see it. What was the name of the... Okay, forgot the name. Forget it. So, I think in terms of the initial grid, it's fine. It takes a bit of time to create, but it's okay. Now the next thing I'd like to do is to rotate each of the triangle based on its positions, based on the column and the rows, number of the rows and columns. If it's an even number, if the columns number and the row number is an even number, then rotates clockwise, and if it's odd number, then rotate counterclockwise. Now, currently all the points are being sticked, or all the primitive are being merged or welded. Okay, so you need to first of all separate those points or make it unique. So to do that, I am going to use a component like facet. Make the points unique so that all the points have been unique, so that you can control each triangle separately. Like these. Previously you couldn't do that. Without this, the triangle just moves along with all the points. So I don't want to do that, so I have made the points unique. Now, next thing, I am going to rotate the triangle using primitive wrangle. Okay, and let's do that. I am going to let me think about, yeah, let's rotate it using primitive wrangle so that I can access each point using primitive for each primitive, and each primitive has its value I and a n value. So rotate, which you could also do that using for loop and the rotate or transform node, I guess, but let's make it hard way. First of all, I'm going to get the list of points from the primitive. Prim_num. Then let's for loop. Let's create a for loop to access each of the point. Just want to rotate all the points in the same manner, either in clockwise or counterclockwise. Let's get the point number, and let's also get the point positions. Let's say I'm accessing to one of the triangles, and I'm currently trying to retrieve the point positions in order to rotate each of the point 0. Oops. I'm using a different keyboard right now, which makes me leads me to a lot of typos. Okay, I have a question from Lemira. would you be able to do it with the point wrangle as well? I'm assuming that would triple the amount of work in this case. You mean creating a grid? Probably. Yeah, you could do that as well. Or if you are talking about rotations, yeah, it's totally possible. But creating the grid might not be suitable for point, because you need to have an initial point, a list of the points in order to create the grid. So currently I don't have anything like that. So I am guessing for the initial grid, using detail might make more sense. Or if there's any like a useful like node already available, like maybe grid, and shifting its dimension, shifting its point to corresponding grid positions might work as well. If you use the grid together with the divide node, you'll be able to have a triangulated grid. Then by shifting the point position of this grid, then you might be able to create a similar grid geometry like I had created, like these. That might be simpler. In that case, you could use point wrangle for sure. And that should be faster as well. Okay, there's no reason why I didn't do that. I just started in this way, so that's the only reason. Okay, now what was I? So I have retrieved the array positions. Let's also try to get the what was I trying to do? The angle, how much I want to rotate. Okay, so float angle, and let's also make it radians. Which means I want to have this parameter as a degree. Okay, let's have this in between 0 to 60 or 120 degrees as a rotation. Okay, actually I don't really need to rotate that much, because later on I'm going to use physics to move its positions based on the physics properties. So I'm going to, as an initial state, I want to make the rotation as small as possible. But this is in this step this is just a parametric pattern creation, so any number will be fine. It also in turns for the testing. So now that I have this angle, let's also create a rotation matrix, starting with the identity matrix, then rotate its matrix by this angle using a z or y axis, which is the upward axis. Okay, now now I can first of all move the current point positions for each triangle by to the negative direction of the center of this primitive, and there is a reason for that. Okay, now the reason is because let's say we have this triangle right here, and I want to rotate clockwise or counterclockwise, and we have this position 1, position 2, and position 3 for each primitive. Okay. And I have retrieved those positions on a for loop, and I have this center point as a at p, which is a attribute that you could get using inside a primitive wrangle. Inside a primitive wrangle, by using at p, you could get the centroid of the primitive. Okay. Now, in order to rotate it, And let's say this is the origin of the space, 0, 0, 0. Okay. Now if you just try to rotate those positions using like a matrix with specified angle, let's say like 30 degrees, and what if you just apply the rotational matrix to this one as it is, then it will rotate using this point as a center axis for the rotation, which will create a angle like these and rotate the triangle like this. But actually I don't want to rotate the triangle like these, but I want to rotate the triangles and locally. So this is a bit of a problem. I don't want to rotate like these. So in order to avoid this one, first thing you want to do is to move this point, to move this whole geometry so that the center point will match with a center space. Okay. So first of all, move the whole triangle like these so that the center point will be at the 0, 0, 0. Okay, which means this position is for each triangle vertices. These are position 1 minus at P, position 2 minus at P, and so on. Position 3 at minus at P. Okay, now moving these triangles to the center, then applying the matrix, then you can now have this local rotation to the triangle and can rotate the triangles clockwise or counterclockwise locally using center as the rotational center. Now the problem is that it's still in the center, so you want to make this back to the original positions, and you can just do that by using the same at P. After you have rotated, you can move this back by saying rotated position 1 plus at P, rotated position 2 at P, and so on. Okay. And as a result, you'll be able to get the locally rotated triangles at the same positions. That's the trick, and that's what I'm going to do now. So first of all, I have subtracted by the center positions of the triangles, then rotate the positions by multiplying the position with the matrix. Then make this back to the same positions by adding at P. Alright. And spell mistake. Met. Okay, so now the position has been rotated. And then, last of all, I would like to apply this updated position to the current point position using setPoint attrib 0, meaning override at P for each point. PT pos. The position is the updated point positions. Now, I'm seeing some caches here. Why do we have that? Let me reopen the file. Sometimes it happens. Okay, now it's gone. Okay, where's my mouse? Right, so if I rotate it, okay, looks like these. So that's good. Now the problem here is that all the triangles are rotating in the same direction, so I want to change that as well based on the I value and the n value, whether it's a odd number or the even number. So currently all the faces are rotating counterclockwise, but I want to change that so that the one that's on the odd number, odd index, will rotate in the other directions for both column and the rows. Okay, so to do that, I need to have two values. One, let's call this value 1 based on the I value, which is the number of columns from the primitive, so I at I, and estimate whether it is a even number or odd number by calculate the remains. If it's 0, then that's even number. If it's 1, then that's odd number. Now I'm going to make a conditions here. If this one is equal to 0, then I'm going to create a ternary conditions, meaning I'm going to create a one-line conditions here. If it's equal to 0, which means it's even number, then I am going to make this value 1 as 1. If not, then make it as -1, so that I can multiply it to the angle to rotate in the other direction. Now do the same for the value 2 for a n value. So I at n, calculate the remains with 2 to see whether it's even number or odd number. If it's 0, meaning if it's even number, then set it to y. If not, -1, same as the I value. Now that I have this value 1 and value 2, I'm going to multiply it to this angle right here. Multiply by value 1 and also multiply by value 2. Okay, now as a result, you can see this triangle and this triangle is rotating in the other direction, and also this triangle and this triangle is rotating in the other direction as well, creating this kind of rotation. Now this itself is also looks pretty nice, but doesn't really give any like geometrical like beauty yet. So after I've rotated, the last thing I need to do in order to create a parametric like opening triangles, I need to move those edges or the vertices so that it stick with one of those triangles, so that I can have a connected triangle tile piece, which also have these openings as well. Okay, so let's do that. In order to do that, I probably need some informations which points are which points connected to which index. So let me see how I should do that. Okay, so first of all, after I have made all the points unique after the facet like these, okay, with before rotating the triangles, I can notice that there are many points, the same points on the same positions, right, like this. But things that I want here thing that I want to know here is the value that I've created right here inside a triangle grid. Before making all the points to unique, I have created this parameter or attribute called I and n for the point as well as the primitive. I've also set the I value and n value to each of the point. Okay, if I want to show you, you can create the marker to visualize it. Let's change the color to red. And so this is for the y, as this is for the I value. So goes from 0 to incremented by 1 to the horizontal direction. If it's n, let's make it blue and hide out the point number. So if it's blue, then it's incremented by 1 in the y direction, vertical direction. Now currently the facet points right here, I'm not sure if this one has its information. Let's see. Actually it has. Yeah, even after it did the unique, I've created the unique points, it still has this I and N, so that's good. That's good. Okay, so but the things that I don't have is the point number, which if you go back to the triangle grid and look back to the point number right here. Okay, start from 0 to, in this case, 399. Now these point number has been destroyed after I have made these facet, after I use this facet to make those point unique. So I don't see these point number related values. So I also would like to have that value as well for some reasons. So let's also apply that. To do that, you could, for example, okay, I cannot see. You could probably, first of all, get all the points except for the primitive just by deleting the primitive and keep the points. Okay, so now I have all the points information. Actually, I might not need to do this after all. And then use the point wrangle to get the corresponding point information. In this case, I would like to get the point number. And transfer that point number into each of the point right here. So to do that, I could, for each point, I could, let's say, first of all, get the new point from the second input with a current point positions. And this near point NPT is the point number actually that you want to apply to each of the point for each of the unique points. So just going to create a attribute like PT index equal to NPT. Okay, that's probably it. Let's make this new point. And let's check this out. Go into the geometry spreadsheet, and now I have these PT index maximum 399. Yeah, that's good. Okay, and probably didn't really need to delete it because I'm just referring to the point. Just gives you the same result, right? It's good. Now connect it back to the rotate. Now's the time to offset the geometry so that I have final parametric geometry, which is still a phase 1. Okay, now let's see, and this is a bit complex to do actually. Now how should we do this? I am going to use the, let's say, point wrangle in this case, and based on the I value or PT index to create an offset. So let's do that. Point wrangle. Point wrangle. Oops. Crashed. Okay, let me try to salvage this file. Where is it? I think I didn't save it, so hopefully I'll have this backup. Okay, so that's my C drive. User up data. local temp and Houdini temp. Okay, let's just close this. Try to salvage it. Okay. Okay, let's see. Wait for a moment. It's opening right now. I think it's not the one. Okay, is it? Oh yeah, it's opening right now. Let's wait for a bit more. Okay, I guess I'm taking too much time on these parametric like surface creation, but well, I thought that I shouldn't skip these part because this itself is also interesting to me. So I have this backup. Okay, looks good. Now let's connect this point wrangle to the rotate to create the shift. Now in order to do the shifting, let's see what kind of information I can use to do the shift. Now looking back to this one, what I would like to do here is to move these triangle. First of all, move this triangle right here. Let's move this manually for now to test out. So what I want to do is to move this point to so that it can stick to this point right here, like this. Okay, and do the similar things for this point, this triangle, which should move in this way so that this triangle will touch in this way, and keep doing it. The next triangle for this one will touch again the bottom left corner like these. Now if you go to the bottom part, this triangle, I would like to make it touch this vertex right here to somewhere around here so that it can connect with these upper triangle on the right top corner. Now for this one, I would like this point to connect with the left top corner like these. And by continue doing that, you'll be able to have a connected triangle piece. Even after you have rotated. But I don't want to do it manually, of course. I want to do it parametrically or algorithmically. And let's think how we could do that. Now, if I look at the current conditions, I can see that the total offset value between these vertex that I want to stick together is the distance is pretty much the same, I think. You can see I can assume that the distance between the vertex which I want to connect is the same for everywhere. But I need to consider that if I move this triangle to this point positions, then I also need to move all the triangles on the right hand side to the same directions and with the same amount to keep the offset distance the same for all the rest. Okay, and after moving all the triangles in these directions, I also need to move the triangles for this one, and all the rest on the right hand side to this direction. Okay, so that's probably what I need to do. Now, in order to start off, what I would like to get is this point vector information. The vector information goes from this point to this point, and also the length of this vectors, and see if I can just use that information to modify it for a whole transformation. Now, to do that, I am just going to retrieve 2 triangles using delete. So just retrieve first two triangles, so 0, 1, and let's delete non-selected so that I have this triangle information. And what I would like to get is the vector value going from this point to this point, and probably apply it to a detail attribute so that I can refer to it later on by looking at the detail. So first of all, I would like to show up the point number. Let's make the guide font to large. Show up the point number. So what I would like to have is the point direction goes from 0.4 to 0.2. Okay. Now let's retrieve that using attribute wrangle. Oops. Make it detail. Let's say direction info. So I just need to retrieve 2 point positions. First point positions is 0.0 p at in this case 2. This one here, 2. Other point position vector pos2 is equal to point. Now I have nothing. I don't have any professions to mathematics or geometry, so probably there are more easy way to like create this using some equations, but I don't have that kind of information myself. I don't know how I can really try to estimate the positions using the geometric equations. Maybe there are, but so what I'm going to do here is a bit more brute force way to find out what's the connections using this vector calculation way, which might not be elegant at all, but that's my limitation for now. Hopefully I'll be able to know how I can do this with more smart way. Probably. Yeah. Okay, so position 1 is this one, position 2 is this one. So position 1 going from 4 to 2, I can create a subtraction for the vector like these. And I have created the directional vector attribute to the detail with these information. Then if I open up the geometry spreadsheet, I should be able to see this detail attribute with this directional value. Now I can use this directional value to try to move each of the triangle at the corresponding direction and values and amount, also using the length of this vector as well. You shouldn't normalize this vector. Okay, now let's connect this to a second input of this point wrangle, and let's try to move each triangle. Okay, so first try. First of all, I'm going to retrieve the directional value from the detail from the second input. So vector direction is equal to detail 1 direction. That's it. Okay. Okay, now I'm also going to retrieve the primitive number for each point because the number of or the amount of values that you want to translate into x and y direction, in this case x and z direction, should be corresponds to the multiplication of the column number or the row number, which you want to access this primitive attribute for I and n. I stands for the column number and n stands for row number for each primitive. Okay. So let's retrieve that as well. First, I need to retrieve the primitive number for the point. I can do that by using a point prims, which will give you an array of primitive which touches with this point. But I know that there's only one primitive touch to each point, so I will just get the first one from the array. Alright. Now let's get the I value and the n value. Int I is equal to prim 0 and I at prim. Int n is equal to prim 0 n prim. Alright. Okay, now this is the stuff that I need to do. Now I need to move each point based on this I value and n value together with this directional value somehow to make these triangles fit into the right positions. Now for these triangles, for the second triangles right here, it is where the I is equal to 1 and this one is I equals to 0. So let's try to move it to the right direction first using this directional value right here. So I'm just going to try to move the point positions at P. Oops. Okay. At P plus equal, which means I'm going to add the value to the point. Okay, first of all, directional value multiply by I and see what happens. Okay, I think I'm seeing some cache here again. Right. Now, the first triangle is at the right position, I think, but from the second, it's not, but the third and the fourth is at the right position. It's connected at the right points. Same for the fifth and sixth, seventh and eighth. Only the set of these two triangles is not connected to the right positions right here. So I want to move the whole two sets, same for all these, offset it to this direction. And if you look carefully, and if you look from the top view, this is actually vertical direction, luckily. So if I just move this whole two set right above, right to the z direction, positive or negative z direction, that will just do the job. And the length of how much it should move, it might correspond to the length of this direction itself. So let's try that out. Now, in order to select only the one that's on the 2, 3, or 3, 4, and 5, 6, and 7, 8, what you can do is to multiply I or divide I by 2, which gives you 0, 0.5, 1, 1.5 to 2.5. And then if you get the floor value of these divided value, then you get 0, 0, 1, 1, 2, 2, and so on. Okay, so and multiply this value by the length of direction going upward, you might be able to get what you wanted to have. So to the negative z direction, and let's create the vector value going to the z direction, 0, 0, and using the length of the direction, meaning the magnitude of the vector as the initial vector values. And you also need to apply set the distance, how much you want to move, based on the in this case I value right here. And as I said, you want to move each of the set of the triangles. And so what I am going to do is to first of all multiply I and multiply by 0.5, make it half size, which will create the floor value, but make it back to an integer using floor, so that the first two will have a value equals to 0. So these triangles, it's not going to move. The second set will going to have a value. With this calculation, you'll have a value equal to 1, and by multiplying 1 by this value, the vector value, this 2 set will go upward by this distance. Therefore, when the I is equal to 2, then you will move upward the double size of this vector, and it looks correct to me with these value. And if I get the value, if I see the result, it goes like these, and looks pretty much it looks pretty good to me as a result. So in terms of the rows, in terms of the orientation on each row, it looks correct. Now I still need to fix the one that's on the even rows right here, or the odd rows, whichever it is. So for those, I think we need to use this n value to fix the positions. So let's see how we could do that. Let's make it one by one, go slowly. Okay, open up. Now I'm going to, so what I need to do is I need to additionally calculate the value right here. And let's see what kind of stuff I could do, what kind of movement I could use for these one. First of all, I could see that there's an offset right here vertically, and I can again assume that the length of the distance between those points is close to or same to the length of this vector. So first thing I would like to try is to move these points to the positive direction to the z using set 0, 0 length of direction multiply by n. Let's see what happens. Okay, now looks better, and we still have some offset, which is these triangles. There's an offset right here, which should move to downward as well. So this is again looks horizontal, vertical direction. Now in this case, we shouldn't move this triangle anymore, but only translate these triangles and rest maybe these 1, 2, 3, 4, 5 triangles and keep this one left. Okay, so let's see how we could do that. Okay, I have a question. Don't understand how you have created the direction with your info wrangle. Okay, let me go back to this detail. So first of all, I'm using this detail angle right here, okay, and I'm showing the point number for each triangles. 0, 1, 2, 3, 4, 5, 6, 4, 5. Now, what I wanted to get as a direction is the direction goes from this point 4 to point 2. Okay, the arrow going from point 4 to point 2. Now, in order to do that, you just need to retrieve the point positions for point position 4 and point position 2, just like it did right here. Then doing the subtraction between point 2 and point 4. If you do the subtraction 0.2 minus 0.4 positions, then you will get the vector directional value. Okay, and that's the one that I have applied as an attribute to the detail by saying v at direction is equal to position 1, position 2. Looking at the geometry spreadsheet at the detail, you'll be able to have this direction applied. That's how I did it, and that's what I'm using right now. Okay, now by retrieving this directional value from a detail from the second input right here, connect it to the second input. Okay, now let's also name this offset. Okay, so as I said, what I need to do as the rest of the stuff, I need to move all these set of 5 triangles as expect for these one triangle that I have offsetted right now, move downward by the same distance but horizontally, I mean the vertically. Okay, so let's think how I could do that. First of all, this has to be the z direction again, and I could probably start by moving. Let's see, looks a bit hard to do. Okay, I'm gonna try out. I'm gonna create a new line so that I don't get confused with other calculations. At p plus equal to a set 0, 0 lengths of direction. Okay, now in this case, I'm going to try to move the triangle based on the the I value, but in this case I only want to move the odd row number. So let's see, that should be multiplied by a I plus 1, calculate the remainder by 2. Okay, now the top part is also moving, so that's not what I want. So let's also have another conditions. N remains by 2 as well. Okay, so the second row looks fine now. Now I do need to move these whole set of rows right here. Currently this rows and this rows is okay. Now this rows and this rows is offset by a height value right here again for each 2 rows. So which is pretty similar to what I did for the I value here. So first of all, I'm going to calculate the similar things that I did here, then try to move downward again. Now this is not smart at all, but it does what it does. So if you just just need a result. This is fine. If it needs to be more elegant, please tell me how we could do that. I don't know. Okay. Then floor n multiplied by, no, n multiplied by 0.5, just like I did for the I right here. And let's see what it does. All right, finally. Finally, I got this result. And now I should be able to rotate into any direction from 0 to 120 to have this rotated pattern. But always the edge is being fixed, always has been pinned together, just making the holes larger, and the size of the triangle kept the same. Nice. Now this itself is, I think, is pretty interesting to create in terms of a parametric model, but that's not just it. If you have more time left, I'm going to show how you could convert this into a physical model. I mean, for the physical simulations using Vellum to create a kind of a custom openings based on its collisions, which could be really interesting. So for now, this looks okay, and let's also create the controller to control some of the parameters that I have set. Controller. I guess I made this definitions a bit too hard to understand. So let's name this one grid X, grid X, grid Y, grid Y, which determines the grid size, the number of grid on X and Y direction. And let's also have the grid size from 0 to 1, and also the rotation value from 0 to 120 as a degree. Okay, apply, accept, and let's have these value copied. Go back to the initial triangle grid, paste it right here. Oops. This one has to be Y, and the size is, why am I having this size have to be the grid size? Okay, I might need to make these values. Okay, this is pretty weird. What's happening here? Let me see why. If I change the number grid X and grid Y to different, then I have some problem here. That might be... Let's go back to see where I did wrong. Okay, this itself is making some wrong result. So num x, probably I'm doing some wrong calculation. Right here. This has to be num x. Alright, okay, phew. Okay, going back to the rotation, let's check this is still okay. Alright, looks good. Now, let's also copy this angle, paste it right here. Okay, so now I have gathered all the parameters that I can control with these for this parametric tile, which works great. All right, now let's go to the step 2 of phase 2 to make it physical, to work with the vellum. And that's what I wanted to do initially. Takes a lot of time till here, but I think it is worth it. First thing I would like to do is to make the initial set or initial geometrical tile to be have a small angle as possible, like this, like 2, 1, because I want to start with the really planar surface, then want to make those pattern opened with a specific collisions to have an interesting effect. So let's make it 2 for now as initial condition. And from there, I'm going to try to create some physical properties. The first thing I would like to do after the offset, in order to connect all these triangles together, currently all the triangles are separated. All the points are unique, so I want to make it back to the connected geometry by using fuse, so that the connected points will be merged together, so that if I try to move one triangle, the corresponding points to the next triangle will follow it like these. Okay, that's good. Now, after I fused it, I am going to make the group for this primitive, the whole tile, as a primitive group. Let's name this triangle, or any name you want, like tile, tessellation, anything. Okay. Now, next thing I would like to do is to so let me just try to convert this straight to a Vellum like object and see what the simulation looks like, which gives you a bit of problem. Just convert it into a Vellum, so you need to have some trick in order to convert it into a Vellum property. Well, let's see what would happen if I just directly use a constraints. So I'm going to use the Vellum configure cloth. So I'm going to convert this into a cloth, a surface, which as a result doesn't give you a bending forces, because no triangle is connected by edge. All the triangles are only connected by the points, which doesn't really create a bending force, but only creates the stretch force. Okay, so, and you can check that by looking at the collision or the constraint geometry coming from the second output of this Vellum cloth. Check here, go to the geometry spreadsheet, to the primitive. If you look at this group right here, you only see the stretch type, but you don't see any bending type, meaning there's no bending like forces, which will cause this close to behave a bit weird when you try to calculate the physics simulations. So let's see how it looks like. What I'm gonna do, I am going to create a Vellum solver. Connect all these. And let's also raise this up a little bit upward and have some collision object so that it can touch with that object. So I am going to move this cloth upward a little bit using transform. Let's say by I don't know, by 1. Okay. Now let's also have some collision objects somewhere around here, beneath the clothes. Let's make it as a sphere to make it simple, and bring it to the center. Make it polygon with some frequency. Let's move this somewhere around. Oops. Somewhere around here, which might be too big, so I'm gonna reduce the size to 0.5. Alright, that's good enough. Let's move this a little bit right. Okay. Now connect this polygon to the third input of the solver, which is going to be used as a collision, which I guess I could do it right here, this way. Alright, so let's see what happens with this without tweaking anything for the Vellum. Okay, and let's also make a floor by checking this one, ground positions to 0, 0, 0. Play it. Okay, I'm seeing the cache here again. Let me reopen the file so that I don't see the cache. I don't know how to delete this cache. Okay, now let's do this again. If I play it, now this kind of a it is collided, and the triangle is being connected by the points, but as you can see, I don't really like its behavior. It doesn't preserve the tile pattern that I've created previously. Okay, it just opens up like pretty randomish. Seems like there's no like cohesion of force to make it to preserve this pattern if it collide with other geometry, which I don't really like it as a output. So, and one of the reason is because this doesn't have any bending force because it's not connected by the edge, but it's only connected by the points. So what I'm going to do here is to create additional like stretch forces, which will prevent these opening to open too much, but try to preserve this pattern itself as it is, and by adding a additional stretch line with a different stiffness value. Okay, so that's what I would like to do here. Now to do that, I want to add a additional like lines which connects the center, these center holes. I want to have these small triangles which connect these points to each other. This is the point where I want to make thinner as possible to preserve this sweet pattern. Okay, in order to do that, I'm going to create a small like kind of a transparent spring right here with a lower stiffness, and which can be extended, which can be like deformed, but still it's connected by the spring, so not too much, with some aspect based on the stiffness. Okay, so that's what I would like to do. Add additional constraints right here for each of the holes. Okay, so let's do that. Okay, I have a question from Antonin. Just 2 little questions. Will you continue to learn algorithmic design series? Will you speak of Vellum in? Yep. If you're talking about the Vex for algorithmic design, I will continue it. right now I'm kind of struggling with a bunch of deadlines. So after I have done with all that, I am going to continue the Vex for Algorithmic Design basic series. Okay, and yeah, would love to do the Vellum as well, but maybe in the different series probably. Since it's, well, it could be related to Vex as well, I guess. So yeah, I would like to do that as well somehow. Sorry for being late. Update. Okay, now where was I? So what I wanted to do is to create these constraints to each of the holes. So to do that, let's see how we could do that. In order to do that, what I could do, so let's go back to the basic triangles right here, which was the which when the angle is equal to 0, okay? And the point where I want to create a small triangle like constraints is at each of the points right here. So meaning I might want to create the line connections for all the points from the basic triangle grid. So which means I already have I already know the total number of like points, which corresponds to the total number of this point right here, which I cannot see it right now. Where is it? I thought by middle click I was able to show the information. Seems I can. I'm getting error for some reasons that I cannot show the informations. I have no idea why. Now, either way, what I need to do is to retrieve the total number of points from this grid and then loop through all the points with this one, maybe before moving it upward. And I can do that by going back to the geometry spreadsheet of this triangle geometry, which has this PT index that I have created previously, which corresponds to the point number of the base triangle geometry. So together with the total number of points and this index, I could create a triangle for each center points for the holes. Let me explain how. I'm going to use another type of wrangle which I don't use that much, which is called as I think I first have to create attribute wrangle as always, and then change the run over to a numbers, which you can use to set the numbers by yourself, number of like loops or number of count of operations by yourself. Currently it runs only 10 times, but the number of operations that I want to run is based on the number of points from the base grid. So going back to the triangle grid, I can try to retrieve the total number of points using expression 1 points, and then look at the triangle grid, which will give you a total number of points, which is currently 440. Okay, so this is the total number of loops that's going to be operated simultaneously inside this code. Now, if there are like tons of points or tons of number of operations to be done, then you might want to also increase this thread job size. But for now, the number of points is pretty low. I think it's fine. Now, let's try to create these lines. So first thing I would like to do is to, so you can first of all access to the, or get the point number or the current count number based on this number attribute by using I at lem num, or maybe you don't need I. At lm num is the corresponding to the pt num or prim num based on its run over. If the run over is equal to numbers, then by using lm num you can get the current index of this loop. Okay. Now I'm going to use this to retrieve a bunch of point numbers from the first input by finding the corresponding attribute. Find attrib val from the point with the pt index attribute. So pt index the attribute that I want to search for, and this is the value that I'm going to use as a search query. And if the pt index attribute and the lm num is equal, then I can get the number of corresponding point numbers. So currently, if I go back to this one, I have a bunch of points which have a same pt index numbers. In this case I have 2, which means somewhere, I guess somewhere around here. Okay, so for points on a grid there's only 2 points. Okay, so in this case you'll be able to have 2 points as an array. Now in this case you have a 1, 2, 3 points, so you should be able to have 3 duplicated points somewhere. If you go down somewhere around here, so these point 166 says there's 3 duplicated pt index, which indicates that there are 3 points right here and the same grid points, the original grid points. Okay, so by using this find attribute val using lm num, you'll be able to find the corresponding like point numbers, either 1, 2, or 3 as a total number for each point. And for each point, then I could use those values to create a triangular or straight lines. If there's just 2 points somewhere around here, then I can just create a single line. If there's 3 points, then I can create 3 lines. If there's 1 point like here, I don't really need to do anything. So I could create the conditions if length of PTS is equal to 2, or else if length of PTS is more than 2, which in this case 3, then I could create the line. Alright, so let's do that. So if it's just 2 points, then I could just create a single line. Int pt1 is equal to pts 0, and pt2 is equal to pts 1. Then create a primitive like as a polyline. Line is equal to add prim 0 0 polyline connecting pt1 and pt2. And let's see what it does. Okay, now you can see that where you have 2 neighbor points, you have the single lines being created like these at the edge. Like these. Okay, and this line is going to be used as a additional constraints to pull together with the small stiffness. Okay, and let's do the other one as well, that for the one that has 3 neighbors. So for these I'm going to use the loop. If it's 3 neighbors, I would like to create a 3 lines, so I can just loop through all the point numbers. Okay, and PT1 is equal to PTSI, and PT2 is equal to PTS I plus 1, and calculate the remains by the total number of PTS, so that if I gets more than the total number of the points, then it goes back to 0. Alright, so that I can get the loop. Now, same for this one, I'm going to create the line between these point 1 and point 2. Okay, now I have created these small triangles right here. Looks great. Alright. Now, the last thing, I'm also would like to set a group to these lines as well, so that I can later on like separate these to apply a different attribute or delete it, because these ones have to be transparent, or I don't want to show it as a last result. So let's set the group, set prim group 0. Well, how should I call this? Pull line, or line. I'll just say line, which might be confusing. Okay, copy this and do the same for these. Okay, let me check the geometry spreadsheet to the primitive, and I have both lines and triangles. Okay, looks good. Now, let me name this to additional constraints. Okay. Now, after I have created the Vellum closed properties, I still need to do something for it, because currently I have created all the lines to have the same stiffness, and I think it does do job that I wanted, which makes these places stiffer to keep its original positions, but currently I think the stiffness is too big. As a result, if I play it, you don't see much of an opening anymore, which is a bit bummer. Okay, and at the last, let's also delete these edges as a visual. Delete the line. So it looks like these right now. So this is a bit too stiff. I want to have more openings to have more variations between the gradient openings result. Okay, so to do that, I need to control the stiffness of these center constraint curves. To do that, you can check the constraints right here coming from the second output when you created the Vellum cloth, and check the geometry spreadsheet to the primitive, and you can go to the one that says line. Okay, it's disappeared, so I guess I need to check based on its rest lengths. The one that rest length is really small, like close to 0, 0.01. These are the one which are newly created to fix the point together, or pull the point together to keep the pattern. And I'm going to pick all these small rest length values, and I'm going to modify this stiffness value right here to make it smaller so that I'll be able to have more openings, more like rubber-like or more elasticity to this constraints. Okay, maybe I could also change this rest length to close to 0 or something as well for all the stuff. Maybe not. Well, let's also try that. Okay, so in order to modify these rest lengths and the stiffness for this primitive, I'm going to connect this second output, which is this constraint, with the primitive wrangle. And based on the condition, based on the rest length conditions, I am going to change its property. In this case, its stiffness, and probably a rest length as well. So stiffness. Okay, so if the current rest length is equal to or smaller than 0.02, which is, or maybe it's also dependent on the total size of this one, the grid size of this one. So I'm going to copy this parameter, grid size, then go back here and have that value promoted or copied, transferred. Okay, so the edge of the triangle is always equivalent to the grid size. So if it's smaller than this grid size, the rest length is smaller than grid size, then I can assume that the edge is the constraint is the one that is used to pull to the grid center. So let's make sure that it's smaller than grid size. So grid size multiplied by 0.1. Okay, which in this case around 0.02 something. Now let's make sure that this is okay. Yeah, maybe to make it safer, 0.5 might be okay. All right, now I'm going to change the stiffness, override the stiffness to something really small. Maybe I can create a parameter as well. And this stiffness is kind of a log scaled value. So for this parameter, I'm going to change the value to a logarithmic float in between 0 to, let's say, I don't know, 1,000 or 10,000. Which might be too big. Let's apply and see what kind of values I get. So first few slides you can get the value in between 0 to 10 or around 10. Then it goes larger really quickly. Now I want to try with the value 1 and see how it looks like for the stiffness. Now after I have override stiffness, I can check that the geometry spreadsheet is changing its value. Okay, for the one that's the rest length is smaller than the grid size. Now let's go back and connect this to override the constraints like these to the second input of this Vellum solver and see how it's going to look like as a result. So this is the previous result without changing the stiffness. Okay, and let's reset it. And currently the stiffness is equal to 1. Alright, now I see what I wanted to see. I have made those openings, the stiffness for these openings triangles to be close to 1 or equal to 1, makes these more elastic, more softer, more be able to pull to, so that as a result you'll be able to create this kind of a more opened pattern. So less stiffness you have, you can make the openings bigger, but if you make it too small, then you'll start to see unconstrained holes again. If I make it 0.0, 0.1, maybe that's too much. Maybe that's not too constrained anymore, in my opinion. How about 10? I make it 10. Now you see a little smaller holes start to appear. So what I would love, maybe somewhere around 1 is the one that I really like. Okay, it's good. Now what if I also change the rest lengths for these stuff to keep it close to 0? Would it work? Let's see. So rest length is equal to 0. Also, you want to change the rest length original rest length reg to 0. Let me check the geometry spreadsheet. And currently, the one that was small enough has the rest length 0 and rest length original to 0. Okay, let's see what would happen with these. If I play it, okay, not much of a change since these are already for enough. It's not really pulling to each other, I guess. If I make the stiffness bigger, then I'm guessing these start to pull to each other as well. So if I make the stiffness to like 1000, the triangle starts to connect to each other. But at the same time, I'm having a little bit of like dancing here. Maybe that was too big. And maybe there are some kind of other constraints happening here other than this rest length. So probably I might not want to change this rest length after all. If I don't have these and keep the stiffness thousands, would it still work? Yeah. Maybe I might need to change something else other than the rest length to make the distance equal to 0. Not sure what. Maybe the compressed stiffness? Not sure. Not really sure. Well, it still works, so that's fine. If you want to make these openings small as possible, then go back to the rotation and make the initial rotation to be small as possible. This one, currently it's 2, make it like 0.5. So the initial openings will be much smaller. And then a bit like these. Okay. And let's make the constraint back to 1. I mean the stiffness to 1. Nice. Nicely done. Okay. And by using this one, you could like try to simulate this fabric-like pattern or tessellation with any like shape. Providing like custom constraints, or make it as a cloth might also be interesting as a future, or fashions and so on. Okay. So that's probably it. That's probably it around that I wanted to show. I could test out several with other geometries for the collision. Let's say can create a box instead of the sphere. Move this. I'll rotate this randomly. And I want to move this as well. Okay, I shouldn't rotate this at this point. Let's move this somewhere around here. Make it rotated. Like these. Okay, let's test it out. This being a constraint or a collision. And let's also move the close a bit more upper direction. And let's also increase the size of the cloth by increasing the number of tiles. Okay, now I might want to move the box a bit as well. Oops. Okay, let's see. Let me see. Okay, well, not so much interesting though. It's doing what it is supposed to do. Alright, maybe I might could add a bit more stiffness for these. Get 3. Okay, that's interesting enough, right? Just like clothes, but having kind of a I don't know, how do I say, the expandable properties to this cloth, which can expand the whole area of the cloth. Alright, that's pretty much it. It's up to you how you want to use it. And by understanding the method that I've explained here, you could probably extend it for many types of tessellations, not just this triangle based one. You could try to add the curves as well, or make it more custom like I show in the Pinterest image, like these, like this one. This is 3D printed. And maybe this one is also similar. Okay, it's a bit hard to find. Well, this one is the closest one, I guess. Yeah, you could also try to simulate these kind of pattern as well, I think, which could be really interesting. Alright, so that's probably it. Thank you for watching. If you have any questions at this moment, I would like to I would like you to ask anything. If not, then I'm going to end the live at this point. Currently it's around 12:20 in Japan time. It's around 2 hours and a half that I did. Okay, so thank you for watching. This is the weekly tutorial that I've been doing more than a year, I think, since it's already 57th. And would like to continue doing it until I get bored. Or if I'm until I'm out of my interest with this algorithmic design stuff. Currently I still have some interest in several stuff, so I would like to still continue it. I am going to upload the file that I've created during the live to the GitHub. You could download it from the link in the video description page. I'm going to upload it later, so you can come back to the video URL later to download the file. And yeah, that's probably it. And I'm also doing a Patreon myself, so if you would like to support me in any way, then I would also appreciate that a lot. Okay, so that's it. Thank you very much for watching this week again, and thank you for all the comments. I also really appreciate that. It's good to have it's good to know that someone is watching, and having some questions is always welcome. Okay, so this is it. See you next week with other topic that I'm gonna bring out. Could be more easier, could be more harder, not sure. But all the stuff that I'm going to bring up is the one that interests me, so yeah. And hopefully you could find it interesting as well. Okay. Yeah, please try to use the one that I showed to render, or maybe as a real physical project or physical product as well could also be used, I think. You might need to add a little bit of edge here as well if you want to do that. But you could also do that. Alright. Okay, so thank you, and see you next week. Good night. And hopefully I'll be able to see you guys next week as well. Night.